coherent spectroscopics and all that.
Thank you very much. The microphone set up and everything working. Good. It's a pleasure to be here, and it's very interesting to hear talks about fields and aspects that I usually don't do. I'm come from the dynamical systems area, and I've gotten interested in the transition to turbulence in pipe flow as a dynamical system problem. But along the way, we've identified sort of various connections and methods that could be useful in other contexts as well. So what I will try to tell you is the things that we did in pipe flow and in other shear flows, the lessons that we've learned, and where we are currently in that kind of system. And what makes sort of pipe flow different from the other flows that you typically study the transition to turbulence in is that it has a couple of peculiar features that make it difficult to analyze. So the standard scenarios, the routes to chaos that you know and familiar with, have to do with, let's say, layers of fluids heated from below, like in the Rayleigh-Benard case, where you have a first bifurcation of the laminar profile to the onset of rolls, then you have secondary bifurcations, and at some points it gets sufficiently complicated in space and time that you call it turbulent. And the same happens in Taylor-Quett if you have sort of counter-rotating cylinders, or co-rotating cylinders, sorry. You again have a cascade of bifurcations that gives you turbulence. In pipe flow, matters are different. And the observations of pipe flow and the differences in phenomenology go all the way back to Osborne Reynolds and the setup that he used in 1883 to analyze this. This is a sketch from one of his papers. This is an image of what they have preserved at the University of Manchester. And this little movie that I'll be showing in a moment is what you can actually observe in this kind of setup. If you have a transparent pipe through which the water flows, and then you inject a jet of dye to visualize what's sort of happening in that system. And then what you see is sort of a very active kind of dynamics. There are periods like currently where you have a straight a line of dye going through the system. That's what you would call sort of a more or less laminar flow. And then you have sort of these ragged ones where you have some kind of turbulence in the system. This is at intermediate flow rates. If the flow rates are very small, then everything is sort of laminar. If the flow rates are very high, then it's predominantly turbulent. But in the transition region, you have this transition between the laminar and the turbulent, and all of this happens more or less irregularly, randomly, and there is sort of clearly a complicated dynamics going on in that system. And the possibility to have sort of the laminar coexisting with this kind of turbulent requires that the laminar profile doesn't have a linear instability. Because if it did, it would be gone for good, and that you can sort of hop between sort of this turbulent and the laminar means that the two must coexist. Another way of sort of seeing sort of the peculiar features of that system goes back to experiments that Derbyshire and Mullin did, also in Manchester, but with a different kind of setup. Almost 18 years ago. So here you again have sort of this setup in the pipe, and there is a huge piston that you can move out with sort of a more or less constant velocity. And by incompressibility, this means that you're prescribing the mass flow through the system. Then you have the possibility of introducing a little perturbation here. And then you follow that perturbation as it sort of swims downstream. And at the end of it, you note whether it's still turbulent or whether the turbulence has disappeared. If it's still turbulent, you say you have made the transition, and then you mark it in red. And if it has decay, it has decayed, and therefore you mark it in blue. And then you can map out this kind of diagram where on the one axis you have the Reynolds number, which is the flow rate. And on the other you have a measure of the disturbance amplitude, which is essentially sort of the amount of fluid that you inject in a prescribed time, which is a measure of the velocity perturbation that you add on top of it. And with the image of the usual bifurcations in mind, what you would have expected is indicated by this dashed line here. You would have expected a sort of more or less smooth manifold that separates the decaying ones from the turbulent ones. But what you find is sort of this scatter plot of red and blue dots, where there is no sharp border between them. You have transient ones, so the ones where you make the transition in red here, surrounded by blue ones. You have sort of decaying ones surrounded by turbulent ones. And actually, if you sort of try to focus on one of these spots and you repeat these over and over again, there will be always small differences in your initial conditions, small differences in your perturbation. And then sometimes you will make a transition and that will survive for that long, and sometimes you don't. So that this transition, this border, this separation between the decaying and the turbulent one is a very complicated one. Now, in order to see sort of how complicated that is, what we did was we developed a model for these shear flows in which we could analyze this kind of boundary in a very, very high precision with lots of data points you could magnify. And then that's the kind of thing that you get. So this is a model mimicking this kind of behavior. And what is indicated here is not sort of just sort of a decay or a turbulent, but what we actually did was we added a perturbation and followed it downstream and then noted how long it was staying turbulent. And so the blue regions here at small Reynolds number and arbitrary amplitudes, they decay very quickly. And then sort of the red ones here live for very, very long. This is 1500 time units. And what you notice is that this transition from the decaying ones to the turbulent ones, it's not smooth, it's not sort of sharp, but it comes with these very intricate folds and these islands where it seems to be decaying more rapidly. So there is this roughness in the system. And to see how complicated that is, if you take this small region here and you magnify, then you begin to see that this whole thing begins to have some fractal features. If you take that region in here and you magnify, and then you see these beautiful striations that you know from chaotic advection, sort of from the folding of manifolds in the phase space of the system. And this then explains why all these experiments are so delicately sensitive on the type of perturbations and on the amplitudes of the perturbations. And why in this transition region, sort of like here, it's very difficult to actually reproduce an experiment. So this is from pipe flow. The same thing has been done in plane Poiseuille flow, and you can also do it in plane Couette flow and other flows. So the question then is, well, if that's the case, I mean, how do we get the turbulence in those systems at all? And we start out with this kind of image of the state space, and then initially the only thing that we have is the parabolic profile. That's indicated here in blue. And the parabolic profile is stable, so no matter where you start, maybe the trajectory that you follow is complicated, but in the end, you end up at the parabolic profile. And what we now have to do in order to sort of get some turbulence in that system is we have to start populating this with other states. And the credo is that in order to have some kind of a persistent turbulence, you need something that this turbulence can hang on to. So you need structures in the state space of the system that can act as a scaffold that can then support sort of the spatio-temporal dynamics in the system. And the simplest structures that you can look for are fixed points, of which there are very few. And there are especially none in pipe flow because everything swims downstream. But if you take out the advection, you go to a co-moving frame of reference, you get a fixed point in the co-moving frame of reference, which would translate into a traveling wave in the lap frame. That's the simplest kinds of things that you can expect. And then you can sort of go more complicated from that. You can connect them. You can sort of have periodic orbits, relative periodic orbits, and all kinds of more complicated things. But you do need something that is persistent. Now, the other thing that is said here is that these structures have to be 3D. Why is that? Well, the moment you start making simplifications, like the things are translationally invariant, or maybe you confine them to some two-dimensional planes, it turns out that none of them gives you something persistent. So the only way to get solutions to the Navier-Stokes equation in pipe flow that is different from the parabola is to take something that varies in all three space directions and in all three velocity components. And these are these exact coherent structures. And they have been identified in pipe flow, in plane wet flow, and in all the other flows that sort of show a transition where the laminar profile is stable, but you still get some turbulence. So we need these coherent structures. This is a few of them, examples for pipe flow. So we see here a cross-section of the pipe. And then we have little arrows that give you the velocity fields in the plane. And then we have a color coding that gives you the modulation of the downstream velocity as you sort of in the downstream component. And what you can see here is that these red regions, where the velocity field is faster than the parabolic profile would be, correspond to regions where the vorticity that you have in this plane moves around like this. So it brings fast-moving fluid from the wall, from the center towards the wall. And this has to be adjusted and moved along, but it's still somewhat faster than the parabolic profile, which is why you get these red high-speed streaks. By incompressibility, you must have sort of the inverse effect, where you pull fluid from the wall towards the center, and that's slow, and this gives you a low-speed streak, and these are the blue regions here. And then for simplicity, what we did in this case is we implemented some discrete symmetries. So here you have a case of 4 high-speed streaks and 4 vortices. Here is one with 6, with 8, and then with 10. And then what you have to do is you have to, all of these are then 3-dimensional. And the way the 3-dimensionality shows up is that you can put them in motion. So you now fix the slice in the lab frame, and then these structures move through. And what you see is that all of them sort of evolve. The vortices move about. And then what is helpful for identifying them in the real flows is that the high-speed streaks are rather stationary and that the low-speed streaks wiggle about. So if you look at sort of these things here, they're first on one side and then on the other. So these low-speed streaks kind of wiggle in the azimuthal direction. So now we have these coherent structures, and these coherent structures then form this scaffold on which the turbulence is acting. And what helped to push all of this was that colleagues in Delft, using 3-dimensional PIV set up by Kars van Dorne and the analysis by Björn Hof, actually could visualize this in the pipe flow. So this is the generic setup. This is the 2 cameras that you need for the stereo PIV. That's an image of the facility, including the laser beams that set up the sheet in which you analyze this. And then this is the same color coding that I had earlier with the red, the modulation in the downstream component, the high-speed streaks at the wall, the low-speed streaks in the middle. And then these in-plane arrows indicate sort of the in-plane velocities and the vortices that you see there. And if you follow this for a while, it's kind of chittering around. But the part that is sort of most prominent is if you look at this kind of structure here, it sort of does the same kind of jiggle that the low-speed streaks in the other cases did. And then you can proceed from there and do a statistical analysis. You should not expect to see these structures exactly, because for that you would need them to be stable, which is what they are not. They are unstable and can only be visited transiently, but you can follow them long enough that you see sort of one period of these structures. Okay. Now, the origin of these structures is in saddle node bifurcations. And this is what one of them does, followed as a function of Reynolds number. So you have the saddle node bifurcation. That's when these structures are first born and created. And because there is a saddle and a node, at least sort of normally, there is the saddle, and the saddle drops in energy. It doesn't approach the laminar profile, but it sort of goes low. And then there is the upper branch, which is sort of the node state in this one. And then this upper branch, as you can sort of see here, undergoes various bifurcations, and then it disappears. So to follow this sequence of bifurcations, what we're going to do is we'll increase the Reynolds number, and then we'll start at a state of 175, and what we have is sort of a periodic orbit. And that's what this periodic orbit is. And then as we increase the Reynolds number, it sort of grows. So that this is going up here. And then comes the period doubling point. And then following that period doubling point, there is another period doubling. And then you go sort of through the chaotic phase. There is the period 3 orbit. That's the periodic period 3 window. And as you get up to something like 188.6, you notice that you have a little bit of this dynamics, and then here it sort of drops down dead. And what has happened there is that you have a crisis bifurcation where the chaotic dynamics of this one collides with its outer boundary. The whole thing rips apart, and your initial attractor turns into a transient chaotic saddle.
Can I ask, this is calculated for the full Navier-Stokes equation?
Oh, this is a calculation for full Navier-Stokes. The system is plain quad flow for geometrical reasons, but by now these calculations have been done in pipe flow as well. But this is really full Navier-Stokes.
Sorry, what's the computation of box size? Is it what's the computation of box size? Combined one.
I think it's a minimal flow unit, so it's relatively small. If you look at this in the state space of the system, then you have the saddle state that sits somewhere here. You have the node state that sits in the middle. And the color coding here is again that of the lifetimes. So the blue outer part is what decays, and it decays fairly quickly. And then the inner part with its dark red here has lifetimes of the order of 1,000, which is the equivalent to infinity. It doesn't decay. The node state sits in the middle of this, and then the saddle state sits on the edge of this domain. And you have sort of a stable manifold that comes in like this, and you have another stable manifold that loops around and comes in like that. And so that's the region in which these states exist. As you increase the Reynolds number, the thing begins to deform. The edge is still here on the outer limit, and then the node sits in the middle of it. As you go a little bit further, it changes, and then it suddenly rips open. This is where the crisis bifurcation happens, and everything that was initially in the interior and lived forever now has access to the laminar region on the outside and can decay. And it starts off by decaying sort of on a very long time scale, which is why this is predominantly red. But if you go a little bit higher in Reynolds number, all you're left with is sort of this laguna of a few of long living states, and then sort of lots of a background in between. So that's the way you start populating the state space with these additional states. So if we look at this as our cartoon, so this is at a reasonably low Reynolds number, when these there is only the parabolic profile. Then you have these saddle node bifurcations. Out of these saddle node bifurcations, you get sort of these separate regions in phase space where you can have a persistent dynamics. Then you have crisis bifurcations where this rips open, it becomes transient. So this is in one part of the phase space, and of course if you change Reynolds numbers, more of this will happen in other parts. I've took the same kind of thing, so you start populating the state space with more and more of these structures. They can overlap, you will get more and more connections between them, and then the lifetimes will increase. And so that's the kind of cartoon that you can get from this. You have the laminar one, which is always there and it's always stable. And then you start populating the space with these coherent structures. And we have means of sort of getting these coherent structures. What this line indicates is that you would like to also see sort of the heteroclinic connections between them, because that's what gives you the temporal aspects of the dynamics. You can visit them transiently, and you can calculate the statistics with which you visit them, And all of this is in reasonable agreement with expectations. Now, if you have this turbulent dynamics there, even if it's transient, and you have the coexistence with this laminar profile, the question arises, what is the border that separates the two of them? How do you go from the laminar to the turbulent? And clearly, since this is stable, you have to add a finite size perturbation on top of that. So what can you learn about this dynamics? And the way we went about that was motivated by these kinds of results. What we did was we picked the Reynolds number, because that's the way you do most of the experiments. You fix the Reynolds number as a system parameter, and then you add a perturbation and you increase the amplitude of that perturbation. And that's what you then get. If you look at the lifetimes of your perturbation, there is a flat plateau down here where everything decays, and then you enter this region where you have this transient dynamics, and then you see very big fluctuations in your lifetimes. And therefore you have a transition from sort of a smoothly decaying part here to this irregular chaotic part there, and clearly there must sort of be an edge of chaos going from the laminar to the turbulent, and that's what we were interested in. So if you now take the small region and you magnify, and then you see, there is a little bit of a slope. So as you move further away from the parabolic profile, you need a little bit longer to return. And then it goes up very steeply, and then you have these ragged parts over there. And that's what you typically see in all of these systems. So the cartoon would be that if you look at the lifetimes versus some measure of the amplitude of perturbation sort of crossing through that region here, you would have smooth parts where everything decays. You would have these irregular ones where you have very long transient lifetimes, and you would have sort of these border points where you hit infinity for the first time. So this is what explains then why there is sort of this roughness in the system shown here. These would be the islands that I showed earlier, and then the fluctuations in the lifetimes would go with that. And then we speculated that since this is, let's say, the laminar regions here all connect to the parabolic profile, so maybe the boundaries are connected as well. So we speculated that these crossings here are a crossing of the stable manifold of some relative attractor in that intermediate region between the laminar and the turbulent, and that if you sort of tracked the trajectories that would take infinite times to decay but not reach the turbulent, they would all sort of end up in that state. So the picture was that there is a laminar, that there is a turbulent region, that there is a boundary between them, and that the way to find this boundary was to really sort of follow the states that cannot make up their mind whether they want to decay or whether they want to become turbulent. So you can track them and limit them in energy, and then they should go someplace. And the way you do this is by actually sort of taking pairs of initial conditions, one of the side that decays, the other side that sort of goes up. Then, because they're exponentially unstable, they will separate, and that's when you start refining. You take sort of another pair, and this way you can approximate something that sort of sits in between. This is what you actually get if you do this. So the dotted one here is one of the decaying ones, and then you notice that this is, as far as the energy is concerned, it's sort of in the intermediate region, continues on for a while. And then if you do move up, you move up much higher, and up here is sort of your turbulence level. And so that way you can track the state that is in between, and in the case of pipe flow, it's a very nice and simple structure. It's something that has sort of a pair of vortices. That's what you have to induce. And then there is a low-speed streak in the center, and there are two high-speed streaks as cushions on the side. And that's actually sort of the typical perturbation that you induce experimentally. If you start injecting fluid from one of the sides, maybe pulling it out at the other, you're really setting up this kind of vortex. And in that sense, it's actually a very good perturbation to trigger turbulence in that system. So let me jump on to the next one. So now we have the coherent states around which the turbulence can form. We've understood why the dynamics is temporally intermittent, because the attractor that you start out with breaks open and it turns into a saddle. So you get the decay. We have learned how we can identify the boundary for these edge states. And now it's the time to sort of go at the interspatial intermittent character. This movie doesn't show. So this was the movie that I showed earlier. And if you now take sort of a time trace of what happens, you get this kind of picture. You have a turbulent burst. It goes laminar, turbulent again, laminar, turbulent. And it looked as if this kind of dynamics was externally induced by noise in the system. Well, it turns out that if you run this system in a sufficiently long domain, you will notice that there is some intrinsic dynamics that gives you essentially the same kind of thing. The origin of this is that turbulence in pipe flow starts out in localized regions. It doesn't spread out over the entire pipe initially, but you can get localized patches of turbulence, and you can follow them as you go along. So this is one of these turbulent patches, and you can see sort of it doesn't really change its length as it sort of evolves down the pipe. Now, starting from these localized patches, there are two elements in the dynamics. So the first one, this is at a relatively low Reynolds number. This is a measure of the transverse velocity fluctuations in the system. So you see it sort of, I mean, this is in a co-moving frame of reference. You see the parabolic profile pushing in here and pulling out at the other side. And you see all its dynamics, and then suddenly it's gone. Let me show this again, because the surprising part is try to guess when it will start decaying. Yeah, I mean, it's sort of happily fluctuating, and it does sort of what these turbulent dynamics would like to do. If you look at this for a segment of it, you can calculate mean profiles, you can calculate turbulence statistics. All of this is nice and fine. Nevertheless, if you follow it long enough, it evaporates. So this is one element of the dynamics that you can have in these localized puffs. And this has again to do with the fact that you don't have an attractor. They can decay. This is another example at a somewhat higher Reynolds number. And it does something else. So now you again have sort of your localized perturbance here. The higher Reynolds number shows up in that the scales are somewhat smaller. But you kind of notice that it begins to stretch out further in the downstream direction. And suddenly you have the nucleation of a new one. So at higher Reynolds number, what can happen is that the system, rather than decaying, it starts nucleating a second puff. So now you have a competition between sort of these two processes. There is the decay for the individual ones, and then there is the possibility for creating a new one. And this was analyzed in a beautiful experiment by Kerstin Avila in Göttingen. So she looked at sort of the time scales for the decay. That's this curve as a function of Reynolds number. And not surprisingly, the time it takes to decay increases very steeply with Reynolds number. The other thing that she looked at was sort of the time it takes for two puffs to split. And at very high Reynolds number, this is sort of a frequent event. And that happens very quickly. Whereas as you decrease the Reynolds number, it takes longer and longer for that to happen. And then there is a crossing point here. And at that crossing point, that's where you begin to have this possibility that a decaying puff gets replaced by a newborn one. And with that process, you can then go from a decaying turbulence on this side to sort of a persistent turbulence on the other side. And that number is about 2040. And what makes these results so spectacular is if you look at these times, they're 10 to the 6, this is 10 to the 7, so this is several 10 to the 7. And this is time in dimensionless units, so it essentially means the length of the pipe relative to the diameter. Now, this pipe has not been built. They typically end at about 10 to the 4, several 10 to the 4 in diameter, but what you can do is by improving your statistics with several tenths of thousands of repetitions, you can sort of extrapolate what can happen up there. Okay. I'll have to be brief about this. What this then means is that this intermittent dynamics between the decaying and the turbulent ones, and sort of the way these patterns evolve, gives the possibility of connecting it to directed percolation. And these percolation type models work as follows. If this is sort of a space coordinate, and time sort of goes upwards, you can sort of have a turbulent patch, and then this turbulent patch in the next time step can persist, or it can nucleate something in its neighborhood. That's the two events that we saw. And then you can look at this as a function of sort of these rates. If this is space and this is time, what you start out with, you have something turbulent, and then it sort of very quickly decays. You may have some that persist for a very long time. If you look at the probability of seeing something, this is on a log linear scale, there is an exponential decay, and that's characteristic for these decay processes. If you go to a different Reynolds number, you notice, well, Reynolds number is translated in these parameters. You know that you see these patches of persistent turbulence. You see some of them decay, but then they get infiltrated from the neighbors. And then what you see is you get sort of a persistent fraction of turbulence in that system. And if you look at what is the fraction of turbulent sites in that system, this is for different sizes of the system, and because everything is, if it's finite size, you see that this transition is smooth. But if you make it big enough, you begin to see something that looks like a second-order phase transition. You can assign critical exponents, and you can compare to what experimental results would be. And so the prediction of the theory is that you have sort of this second-order transition here, and this is what the experiments had so far. And it's sort of compatible with this, except that in order to really go to lower fractions, you need bigger and bigger systems, and the experiments end at about 15 to 20%, and that's not good enough yet to really confirm that this is a second-order transition and not, as was indicated here, a first-order transition. There is a latest batch of experiments that brings this down, and it's, in that sense, consistent with a second-order one. So, this was a tour de force, but if you have questions, I'll still be around for a while. So to sum up the kinds of insights that we've gained about this transition to turbulence in pipe flow and other shear flows, is that we do need these coherent structures. They are sort of essential before we can get anything turbulent, and we have to sort of find them, and they're all there in all these systems, and we have to look at their entangling. We've identified sort of what the boundary between these, through these edge states, through stable manifold, really divide sort of the turbulent and the laminar. And then there is sort of a spatiotemporal intermittency in these systems, which is a consequence of the intrinsic dynamics. It can be helped by noise, but it's essentially also a consequence of the intrinsic dynamics, and that one has some connections to directed percolation. So with this, thank you very much. I'd be happy to take questions.
Thank you for very clear talk. Questions, comments? Yes?
Yeah, you're presenting a very different picture. I mean, you know, in the prevailing view, these coherent structures are related to intermittency, but they're sort of perturbations on a simple cascade that flows through the stuff. And you're presenting them as being really essential to everything that happens.
Let's see, I mean, there is a difference in Reynolds numbers by a factor of, let's say, 10 to the 2, 10 to the 3. I'm doing this on the order of 2,000 in the transitional regime. What you have in mind with intermittency and cascades is at Reynolds numbers of several hundred thousands. I don't have anything to say about that yet. That's the main difference. Okay, and then one can go on from there.
Other question or comment? Yep.
Can you remind me what the edge states were that you said?
The ones at the boundary between the laminar and the turbulent. Where are we? This one. So you have the laminar, which is stable, you have some kind of turbulence up there, and you would like to know, I mean, what separates one from the other. And then there is a surface that divides this, and that surface happens to be the stable manifold of something that sits right there. Well, I'm happy to call it a surface, but I'm sure that there are sort of some mathematical subtleties someplace which make it sort of more complicated. I guess what we do know is that at least in the neighborhood of this object, it's nice and smooth. If you go very far away, then it could be a different matter.
More questions?
Could you make any link between the UDEC solution, so UDEC coherent structure, and some sort of the spatial temporal intermittency? Or?
Yeah, that's the part I was sort of brief on. The coherent structures that I showed were periodically continued and infinitely extended. And by now we know how to sort of take these infinitely extended ones, do a perturbation analysis around them, and get something that is localized. So we now have localized structures that serve the same role in, in spatially extended systems. You don't need the infinitely extended ones to localize do the same job.
Okay, we'll send the speaker again.
Thank you.